Today's topic is going to be rational zeros. This is section 6.6. Let's get started. I'm going to reiterate something that I did in the last lesson. In the following lessons, we will be trying to describe a graph of a function without a graphing calculator. You are going to become a detective, and you have an equation. And when you have the equation, you're going to do some analysis on this equation to find attributes of the graph. So I'm going to ask you to do this as if you didn't have a graphing calculator. Means show your work as if you didn't have a graphing calculator. You're going to find the zeros by using the equation as the guide instead of using what it looks like on your graphing calculator as a guide. If you remember, those zeros are where it crosses the x-axis. We're going to be finding out techniques to be able to find how many zeros there are and to find out how many positive zeros and how many negative zeros there are. Before we do that, the title of this was to find the rational zeros. So let's review the number system so that we can even know what rational numbers are. So in your life, when you first started to count, you were young and you started with 1. 1, 2, 3, 4, 5. These were the counting numbers. And you kept going. Eventually you had the understanding that this just went on forever. Then eventually someone took away something from you and you got the idea that there was a 0. So the whole numbers include the numbers 1, 2, 3, 4, and 5 and all the way up. But they now go a little bit further. They include the number with the whole, the 0, the whole number. As you got older, your number system expanded. It expanded to include the negatives. It still includes 0, 1, 2, and 3 going forever this direction, but now it includes the numbers going -1, -2, and -3, and forever backwards. So now the integers, which includes the whole numbers in the counting, include all the positives and negatives. Notice that we do not have any fractions yet. That's what comes next. These are the rational numbers. These numbers are the ones that have ratios or can be included as fractions. They still include the integers, all the negatives and positives, 0s, 1s, 2s, and 3s. But now, in between each of the numbers, we now have the fractions 1.5 or 1.5 and all the decimals in between 1 and 2. So now our number system has expanded immensely. In between each integer, there is an infinite number of numbers now. And so we also have all the numbers that are going backwards with the negatives, but now we have fractions. These are all called the rational numbers. There are still some numbers that don't quite fit. Numbers that cannot be written as fractions. Those ones are like pi or square roots of, let's say, square root of 2, square root of 5, not the square root of 4. That is a rational number. It's because it can be turned into 2. These numbers don't quite fit into, they don't fit all up here, but they're called the irrationals. And until a couple weeks ago, this is the number system that you knew. And we called these the real numbers. But recently, you learned about the square roots of negative numbers. You learned that there were imaginary numbers. And these imaginary numbers do have applications in what I'm going to call the real world. And they are outside of the real numbers. So the new system that we're going to be talking about is called the complex numbers. And this number system includes all the real numbers and the imaginary numbers. For today's topic, we're going to be talking about those rationals. Those rational zeros. It's placed on the number on the graph where it crosses the x-axis with rational numbers. We're not talking about those square roots or those irrationals, and we're not talking about the imaginaries. We're going to talk about the rational zeros. So what does even these zeros look like on the graph? So let's do that first. So for the next problems here, we're going to ask some questions. And if you remember, I told you that we were going to do this without our graphing calculator. But that's very abstract when you can't see it. So we're going to actually first look at a graph and analyze what these zeros are and what they look like, and do a little bit of review in addition to that. So first of all, the question is, what is the degree? Is the degree odd or even? In this particular graph, since one goes up and one goes down, this is going to be an odd degree. The next question is the leading coefficient positive or negative? When we were doing linear equations, if it went up from left to right, it was positive. And if it went down from left to right, it was negative. This rule still applies. This is going to go, it's going up in this direction from left to right, so it's a positive leading coefficient. How many real zeros are there? The real zeros are the number of times that it crosses the x-axis. This is the x-axis. And it crosses that x-axis 1, 2, 3 times. So, how many times does it cross the x-axis? It crosses it 3 times. How many positive zeros do we have? The positive zeros are the ones that are on this side of the x-axis, while the negatives are on this side of the x-axis. So the zeros that are on the right side of the x-axis are 2. That's how many positive zeros we have. We have 2. And how many negative do we have? 1, because it's on the left side of the x-axis. Let's do another one. Same questions. What is the degree, or is the degree even or odd? Well, since, again, it's going in opposite directions, this is an odd degree. What is the leading coefficient? The leading coefficient, it's going from down to up. It is a positive leading coefficient. How many real zeros are there? The real zeros are how many times it crosses the x-axis. The x-axis is right here. It crosses 1, 2, 3, 4, 5 times. So the real zeros are 5. How many positive zeros are there? The positives are on this right side of the x-axis. There are 2. And how many negatives are there? That's on this side of the x-axis. And there's 1, 2, 3. So there are 2 positives and 3 negatives. Let's do another one. Same questions. Is the degree odd or even? Since they're going together, this one is not odd. This one is even. And the way we decide if the leading coefficient is positive or negative, how we did it with parabolas. Parabolas, if they both went up, it was positive. If they both went down, it was negative. And so this one, since both of these go down, it's negative. How many real zeros are there? We count how many times it crosses the x-axis. 1, 2, 3, 4. So the real zeros are 4. How many positive zeros are there? The positive zeros are is where it crosses on the right side of the x-axis, and it's 1. How many negatives are there? It's on the left side of the x-axis. 1, 2, 3. There was 1 positive and 3 negatives. Now that we've seen what it looks like when we're talking about the zeros, we're talking about the positive zeros and the negative zeros, we're now going to find out how to actually discover those zeros. And one of them is by the rational root theorem, or talking about the rational zeros. First of all, let's just review again what the rational number is. A rational number is a number that can be written as a fraction, both negatives and positives. A 0 is where it crosses the x-axis. So together, if I put the word rational and 0 together, it would mean the zeros that can be represented by fractions, both negative and positive. So this would mean I would have no irrational numbers or no square roots in my zeros. Here is the rule. This is something that I'm going to be dissecting in some examples also. So the wording that's here is going to be a little bit hard to understand at first, but once we go over it a couple times, you'll be able to read this again and understand what it means. For a given polynomial function, the rational roots will be given in the form p over q, where p is the factors of the last or constant term, and q is the factors of the leading coefficient. The p over q is a fraction. We said we were going to have rational roots. That means we're going to have fractions. And it's defining what p is, and it's defining what q is. P is all the factors of the last or constant term, and q is the factors of the leading coefficient. Let's do some examples so we can see how that works. Number 5. Number 5 states or says that we need to state the possible rational zeros for each function. If you remember, that definition said we were going to have a p over q. And that definition said that p was the factors of the constant, or the one at the end, the last term, the constant. So we're going to take that 20 and we're going to list all the factors. That means we're going to list what multiplies to be 20. And I like to list them in order, and I like to start with 1. I know that 1 and 20 multiply to be 20. And we can take all in positive 1 and negative 1, so we have to do the positive and negatives of both of those. Then I start with 2, and 2 and 10 multiply to be 20, and I need the positives and negatives for that. 3 does not, 4 does not, but, 4 does. And 4 and 5, I come together in the middle, I'm done. I have all the factors of 20. Now q was the factors of the leading coefficient, which is 2. And what multiplies to be 2 is 1 and 2, and the plus and minus of that. And so now I need to take all of these and divide all the p's by all the q's. So I'm going to do that first by taking 1 and dividing it by 1, and 1 and dividing it by 2. Then I'm going to do 2 and divide it by 1, then divide it by 2, and write all these down. Now some of these are going to be redundant, and we won't have to write them down. So let's start with 1. 1 divided by 1 is 1. And 1 divided by 2 is 1/2. And I need to write the plus and minus for it. We've done 1. Now let's move on to 2. 2 divided by 1 is 2. And 2 divided by 2 is 1, but I've already written it, so I don't have to write that one. Let's now move on to 4. 4 divided by 1 is 4. And 4 divided by 2 is 2, but I've already written it, so I don't have to write it again. Let's move on to 5. 5 divided by 1 is 5. And 5 divided by 2 I have not written yet, so I must write it down as 5 over 2. Let's move on to 10. 10 divided by 1 I have not written down yet, which is 10. And 10 divided by 2 is 5, and I've already written it down, so I don't have to write that one. Move on to the 20. 20 divided by 1 is 20. And 20 divided by 2 is 10, and I've already written it, so I don't need to do that. So your answer for all the possible zeros are 1, 1/2, 2, 4, 5, 5 over 2, 10, and 20. These are all the possibilities for the zeros where it crosses the x-axis with the rational numbers. Now, eventually you're going to have to actually find the real one, the ones that do work. And we're going to do those together in a little while. It seems like there's a lot here. It seems like there's 2, 4, 6, 8, 10, 12, 14, 16 of them. But compared to guessing just any random number, 16 is a lot better than guessing from infinity. So these ones, there is a lot there to write, but it's better than writing every number that there is possible out there. All right, let's do number 6. Number 6, we're going to do all the possible rational zeros. We're going to do P over Q. P, if you remember, is all the possibilities or all the factors of the constant. So we're going to do 8. That's 1 and 8, 2 and 4, and the plus and minuses of those. And then the Q is the factors of the leading coefficient, which is 6. Plus or minus, we got 1 and 6 and 2 and 3. And all the plus and minuses of those. And now we need to find all of those possibilities and divide all of them, all the numerators by all the denominators. So we're going to take 1 and divide it by every one of these. And we will get 1 over 1, which is 1. 1 over 2, which is 1/2. 1 over 3, which is 1/3. And 1 over 6, which is 1/6. And we will have all the plus and minuses of those. Now we need to take 2 and divide it by 1, which is 2. We'll need to write that one down. And 2 divided by 2 is 1, and we've already written it down, so we don't need to. And 2 divided by 3, we will need to write that one down. That's 2/3. And then 2 divided by 6 reduces to be 1/3, and we've already written that. Don't forget that we need to write the plus and minuses of these. Now we need to do the 4. And we're going to do 4 divided by 1 is 4. We need to write that one down. And 4 divided by 2 is 2. We've already written that one down, so we don't need to. And 4 divided by 3, we do need to write down. And 4 divided by 6 is 2/3, and we've already written down, so we don't need to. Last, we need to do the 8. 8 divided by 1 is 8. We'll need to write that one down. We haven't done that one yet. 8 divided by 2 is 4, and we've written that one down. Don't need to write that one. 8 divided by 3, we have not written down. And 8 divided by 6 is 4/3, and we've already written that down. So don't forget your plus and minuses of everything. And here is our answer. for number 6. All the possible rational zeros. This is where it could cross the x-axis. Let's move on now to find all the possible positive or negative zeros. We looked on the graph, and if you remember, the positive zeros are where it crossed on the x-axis on the right side, and the negatives is where it crossed on the left side. There was a man named René Descartes, and he had the genius to analyze these graphs, these equations, and find the strategies to find the positives and the negatives. And so we've got some rules that he has come up with. Descartes' rules of signs is used to determine the number of real zeros of a polynomial function. It tells us the number of positive real zeros in a polynomial function f of x is the same or less than by an even number as the number of changes in the sign of the coefficients. We will do an example of this, but I need you to keep this. I have sent this to notes for you to have this in front of you so that if you forget what I'm talking about, you can look back on this and say, oh yeah, it's the change of the signs. At this moment, you won't know what that means until we do some examples. Next, the number of negative real zeros of f of x is the same as the number of changes of sign of a coefficient of the terms of f of negative x, meaning I substitute a negative x in, or less than this by an even number. Let's do number 11. We're going to state the possible number of positive and negative zeros of the function. We're going to use Descartes' rules. We're going to do this in a very systematic way. First of all, I'm going to write all of the exponents. I have an exponent of 6, 4, 2, and 0. And then we're going to write all the signs right below them. I've got a positive right here. This is positive. It's invisible. I have a positive here, a negative, and a negative. So when I'm testing for the positive real solutions, I look here and I have one sign change. So I have one sign change. Now when I'm doing the negative sign changes, I have to plug in a -1. And these exponents are really going to help. These exponents are going to help because whenever there's an even exponent, it keeps these signs the same. Whenever there's a negative exponent, it switches it. So here's the reason why. If I have a negative x and I plug it in, if I have negative x 6 times, this will turn into a positive x. This will be positive, that will be positive, and that will be positive. And all the positives will be a positive x. So if I have an even number on that exponent, it's going to turn it into a positive. Otherwise, it'll turn it to a negative. So in other words, it'll keep the sign the way it is. So this is an even number, so it's going to stay its original. This isn't even, so it's going to stay the original. This is even, so it's going to stay the original, and that one just automatically stays. So if I'm testing now for the negative, there is still only one sign change. So there is one positive possible root and one negative possible root. Let's do number 12. I'm going to do the same thing. I'm going to write the exponents down. I'm going to write a 7, a 6, a 5, a 4, a 3, and a 2. I'm going to write the signs. This is a positive, a negative, a negative, a positive, and a negative. I am testing, using these to test how many positive real zeros, and I look for sign changes. There's 1 right there, 1 right here, and 1 right here. There are 3 sign changes. So I have 3 possible positives. But if you remember the rule that's listed down here, the rule says that it's also or less by an even number. So I subtract 2 from that and I get 1. Oops. So I could have 3 or 1 possible positive root. To do the negatives, I'm going to have to move this up a little because there's not enough room down there. To test the negatives, I go down underneath, and whenever it's an even number, it stays the same. But whenever it's a negative, it changes to the opposite. So since 7 is positive, is odd, it becomes the opposite. And the 5 becomes the opposite, and the 3 becomes the opposite. But all the evens stay how they are. And I check for sign changes. I have 1 and 2. But I also have to reduce that by an even amount. So I go subtract 2, I get 0. So I have the negatives, I have 2 and 0 as a possibility. And for the positives, I have 3 as a possibility. All right, now that we know how to find the possible rational zeros, now we're actually going to use those to help find where it really does cross the x-axis. So we have the possibilities, but we want the actual zero. So let's get started. We're going to do number 19. Number 19, we're going to do P over Q. And P, if you remember, was this one here. And 1 just has plus or minus 1. And 4 has plus or minus 1 and 4. But 2 and 2 is in there also. So 1, 2, and 4 are the factors of 4. And our possible roots are 1 over 1, 1 over 2, and 1 over 4. I'll write the plus and minuses in a moment. And that's all. I'm going to actually simplify this and put just 1 plus or minus in the front right there. Now, we have 6 possibilities here. 1, 1/2, 1/4, -1, -1/2, and -1/4. And we're going to try to find all of the zeros. So to do this, we're going to divide until we get a 0 remainder. So we need to pick one. I personally like ones without fractions, so let's see if we can do that one first. We're going to take the coefficients here, doing our synthetic division. We have a 4, -8, 5, and -1. And I'm going to pick 1. Our goal is to get a 0 as a remainder. If we get a 0 as a remainder, we know it's a factor. Bring down our 4, multiply, we get 4, add, we get -4, multiply, we get -4, add, we get 1, multiply, we get 1, and we get a remainder. We got it. We got it. So we know that one of the zeros is 1. We now have a quadratic. 4x squared, we got that from here, minus 4x plus 1. We now can do the box method on this one to find the other zeros. Or we could do synthetic division again. With this, and guess again, maybe 1 works again, or maybe -1, or maybe a half or a fourth. So you can do either one of those. It's up to you. I know, I don't like to guess, and I know that we can do the box method on this one, so let's do that one first. I think that's the best way. So I'm going to do the box method here. 4x squared, that could be 2x and 2x, and 1 and 1. Does that give me -4? Well, I'm going to have negatives here. And so When I do that, I'll get negative 2x, and another negative 2x gives us, yes, that middle term, negative 4. So I have 2x minus 1 and 2x minus 1, and those are going to equal 0, so I set them equal to 0. And solve. And so I have 2x minus 1 equals 0. Add that to the other side. I get 2x equals 1 and divide by 2. And x is going to equal 1/2. And I'll get another 1/2 right there. So I'll get 2, and I only don't have to write it twice. So notice one of the possibilities was a half. Here we go. 1 and 1/2, and that one is just a double. It just happens twice. Let's do number 21. Number 21, we need to do our P over Q to find our possibilities. 6 is the first one. It's the P. And 6 has 1, 2, 3, and 6, and all the plus and minuses of those. And 2 has 1 and 2, and the plus and minuses of those. So the possibilities are 1 over 1, 1 over 2. 1 and 1/2. And 2 over 1 and 2 over 2. 2 over 1 is just 2. But 2 over 2 is 1, and we've already listed it. So now 3, we have 3 over 1 and 3 over 2. 3 and 3 over 2. And then the last one, we have 6 and 6 over 2. That's 6. But 6 over 2 is the same as 3, so we don't have to write it. And don't forget that we have to list all the plus and minuses of all of those. All right, so our goal, though, is yes, we've done state all the possible rational zeros. We've done the first part. But now we need to find all the real rational zeros, or find all the rational zeros, excuse me. And so we're going to do that by dividing and using these to divide by until we get a zero remainder. So we're going to go 2, 13, 18, and 6. And we have to pick until we get a 0 as a remainder. If you don't get a 0 remainder, you pick something else. Let's try 1. It's the easiest, I think. Bring a 2 down. Multiply, we get 2. Add, we get 15. Multiply, we get 15. Add, we get 33. Multiply, we get 33. And obviously, we do not get a 0. So we have not picked the right one. I think we need to pick a negative because those numbers kept getting bigger and bigger. So let's try that. We're going to go 2, negative 2, which will be 12, 11. We'll have a negative 11 when we multiply. Then we're going to have 7. Multiply, we'll get negative 7. We're getting close, but it's not 0. So 1 is, and negative 1 is not an option. So what do you want to try now? Maybe 2, because those fractions are not something that I might want to try. And I am going to learn from the negative is the one we need. Bring down the 2. That'll be negative 4, which is going to be 9. Multiply will be negative 18, which will be 0, which is 0 will still not give us to us. Well, we could keep picking numbers. We have to keep picking numbers till we get a 0 as a remainder. And so it seems like the 3 and the 6 are going to just keep getting bigger and bigger numbers. So maybe we do have to use a fraction. Fractions are not too bad. Let's try it. We're going to do the 1/2. Let's try bring down a 2. Half of 2 is 1. Add, we get 14. Half of 14 is 7. add, we're going to get 15, we're going to get not 15, 25, excuse me. Half of that's definitely not going to be 6. So maybe we need to do a negative. Remember, we're trying to get a 0 as a remainder. You just got to keep trying until you get it. We're going to bring down a 2. We take half of 2, which is 1, but do the negative. It's going to be 12. When we add, half of 12 is 6, but we have to do a negative. We get a 12. Half of 12 is 6. Voila, we got it with a negative 6, which is 0. So here is our rational 0, which is 1/2. X equals negative 1/2. Now we have to keep going. See if we can keep going. Or we know that this is a quadratic. 2x squared plus 12x plus 12. And try to do box method with it. So 2x is going to be 2x and x. And 12 is 6 and 2. Or 3 and 4, and we got to try all these. Now, I want you to just know something. The box method doesn't always work, remember? And sometimes you have to do, if the box method doesn't work, what we did is we did the quadratic formula. But the quadratic formula does not give us rational roots. So if this doesn't factor, we're done. Let's try 6 and 2. This gives us 4x and 6x. That's 10. That's not what we want. Let's switch the 6 and 2. We get 12x and 2x. That's 14. That isn't going to give us the 12 either. We've tried the 6 and 2. Let's try the 3 and 4. This is going to give us 8x and 3x. That's 11. That's really close, but not what we want. Let's switch the 3 and 4. I'm going to get 6x and 4x. So it's going to give us 10x. It's still not going to work. So it looks like this doesn't factor. So our only answer is x equals negative 1/2. All right, in this lesson, we learned how to find all the possible rational zeros. We learned how to find the negative rational zeros and the positive rational zeros. After we found the possible zeros, we used those to find the actual zeros. Goodbye.